In today's video, we'll learn about torque and angular acceleration. We can see that there's a relationship between torque and angular acceleration. Is when an object is subjected to a net torque, it undergoes an angular acceleration that is directly proportional to the net torque. So if we multiply each side by r, we get the equation that the sum of the torque is equal to the mass times the radius squared multiplied by angular acceleration. And from this equation, we can figure out the moment of inertia. We know that the net torque of an object is the same as the sum of the individual torques on all particles. And since all the particles have the same angular acceleration, the angular acceleration is not included in the sum of the moment of inertia for the whole body, which gives us inertia is equivalent to the sum of the mass times the radius squared. And so we can substitute our mass times our radius squared for I to get the sum of the net torque to be expressed as the sum of our torque is equal to our moment of inertia times our angular acceleration. When we're asked to find the moment of inertia for various rigid objects, we see that our moment of inertia differs depending on the rigid object that is being examined. And some of the most popular images and their moment of inertias can be defined in the picture below. In our first example, we have a mechanic who is spin balancing an automobile tire, which has a radius of 0.36 meters. By placing it in a machine which applies a torque to accelerate the tire to a speed equivalent to traveling 95 kilometers per hour, the tire has a mass of 32 kilograms and has a moment of inertia equivalent to a hoop of radius 0.31 meters. How much torque must the machine apply to the tire to bring it up to speed in 15 seconds? We know that the radius of the tire is equal to 0.36 meters. The velocity of the tire is 95 kilometers per hour. The mass of the tire is 32 kilograms. And that the radius of the hoop is 0.31 meters. And we're asked to solve for the net torque exerted on the tire over a period of 15 seconds. So we have an equation that states that the sum of our torques is equal to our moment of inertia times our angular acceleration. We're given that the moment of inertia of the hoop, which is expressed as the mass times its radius squared, which we can plug into our equation. However, our angular acceleration isn't given to us. But we know that angular acceleration is the same as taking our angular speed dividing by our change of time, and that angular speed is defined as velocity over radius, which we can plug our angular speed into our equation for angular acceleration, which will give us our angular acceleration be equivalent to a velocity divided by the radius of the tire times our change in time, which we can then plug into our equation, which will give us a final equation of mass times radius squared multiplied by velocity divided by the radius of the tire multiplied by the change in time. And if we plug in the values that are known, we know that the mass of the tire is 32 kilograms. We know that the radius of the hoop is 0.31 meters squared multiplied by our velocity of 95 kilometers per hour. However, we have to convert our kilometers per hour into meters per second. So for 1 kilometer, we know there are 1,000 meters. So we see that our kilometers will cancel out. And that for every 1 hour, there are 3,600 seconds for each hour. Divided by the radius of our tire, which was 0.36 meters, multiplied by our change in time of 15 seconds. And when we multiply our equation out, we see that the torque applied to the tire is equal to 15 newtons multiplied by meters. In our second example, we see that there is a 150 kilogram merry-go-round in the shape of a uniform solid horizontal disc of radius 1.5 meters. It is set in motion by wrapping a rope around the rim of the disc and pulling on the rope. What constant force must be exerted on the rope to bring the merry-go-round from rest to an angular speed of 0.5 revolutions per second in 2 seconds? So once again, let's start by summarizing the information we're given. We know that the mass of the merry-go-round is 150 kilograms, and that the radius of the merry-go-round is 1.5 meters, with a initial angular speed of 0 revolutions per second and a final angular speed of 0.5 revolutions per second over a period of 2 seconds. And we're asked to find what force must be exerted on the merry-go-round. So we know that torque can be defined as our moment of inertia times our angular acceleration. And we're trying to solve for force. And we know that torque is nothing but force multiplied by its radius. So we can rewrite the equation like so. And if we're trying to solve for force, we can rewrite the equation where our force is equal to our moment of inertia times our angular acceleration divided by our radius. And it says that the merry-go-round is a rim of a disc, and the moment of inertia for a disc is equal to 1/2 mass times radius squared times our angular acceleration divided by our radius. And we see that, and in order to figure out our angular acceleration, angular acceleration is equal to our change in our angular speed divided by our change in time. So our final angular acceleration was 0.5 revolutions per second divided by 15 seconds. And since it's in revolutions per second and we want it in radians per second squared, we'll multiply it by 2 pi over 1 revolution. So we see that revolutions will cancel, and we'll be left with an angular acceleration that is equivalent to 1.571 radians per second squared. So if we plug in our value for our equation for our angular acceleration, we can calculate our force. So we have 1/2 the mass of the merry-go-round, which was 150 kilograms, multiplied by the radius of the merry-go-round, which was 150 meters squared, times the angular acceleration of 1.571 radians per second squared, divided by the radius of the merry-go-round, which was once again 1.50 meters. And when we calculate this, we'll see that the force that must be exerted on the rope must be equal to 177 newtons.